Hey guys, how's it going? Mr. Mitchell here. In this video we're going to go over question 3 from the 2024 SQA Advanced Higher Physics exam paper, so let's get started. Question 3 says a wind turbine is used to generate electrical energy from the kinetic energy of the wind. The wind turbine comprises a tower and a rotor assembly. The rotor assembly consists of 3 identical blades attached to a central rotating hub as shown in figure 3a. So there's the central rotating hub in the middle and we've got the 3 blades. It says each blade has a mass of 2.0 times 10 to the 4 kilograms and a length of 54 meters. Each blade can be modelled as a solid rod rotating about its end. The mass of the rotating hub is negligible compared to the mass of the blades. Part A says show that the moment of inertia of the rotor assembly is 5.8 times 10 to the 7 kilogram meter squared, and there's 2 marks available here. Well, we were just told that the mass of the rotating hub is negligible compared to the mass of the blades, so the total moment of inertia is going to involve the mass of the blades, and we were told that each blade can be modelled as a solid rod rotating about its end. So that means that for one rod, the moment of inertia of the rod is what we're trying to find, the mass m is 2.0 times 10 to the 4 kilograms for each rod, and the length L is 54 meters. So writing down our equation for the moment of inertia of a rod rotating about its end, we have I rod equals a third ml squared. Substituting in our numbers, we get a third times 2.0 times 10 to the 4 times 54 squared, and putting that into your calculator should give you an answer of 1.944 times 10 to the 7 kilogram meter squared. But remember, there's 3 rods as part of this rotor assembly, so we could say that for 3 rods, the total moment of inertia I is equal to the moment of inertia of one of the rods times by 3. So we have 1.944 times 10 to the 7 times 3, and if you put that into your calculator, you should get an answer of 5.8 times 10 to the 7 kilogram meter squared, which we were asked to show. Part B says when the wind speed reaches 25 meters per second, the angular velocity of the rotor assembly is 3.7 radians per second. At this velocity, brakes are applied to bring the rotor assembly to a stop. The brakes apply a frictional torque on the rotor assembly. The rotor assembly comes to rest in 550 seconds. Part 1 says calculate the angular acceleration of the rotor assembly during this time, and there's 3 marks available here. Well, writing down what we know from the question, first of all, we don't know what the angular displacement theta is. We know that initial angular velocity omega naught is 3.7 radians per second. The final angular velocity omega is 0 radians per second since the rotor is brought to rest. The angular acceleration alpha is what we're trying to find, and time t is 550 seconds. So let's put a star next to alpha since that's the one we're trying to find. Now, using our equations of angular motion here, we want to use the one that doesn't have theta in it. So we could say omega equals omega naught plus alpha t. Substituting in the numbers gives 0 equals 3.7 plus alpha times 550, and then to get alpha on its own we need to take away 3.7 from both sides and then divide both sides by 550. So doing that in your calculator should give you an answer of alpha equals minus 6.7 times 10 to the minus 3 radians per second squared. B part 2 says calculate the magnitude of the unbalanced torque acting on the rotor assembly during this time, and there's 3 marks available here. So writing down what we know from the question, we're trying to find the unbalanced torque tau. We know the moment of inertia of the assembly is 5.8 times 10 to the 7 kilogram meter squared, and the angular acceleration alpha is 6.7 times 10 to the minus 3 radians per second squared, where we don't really need to use the negative here, but you can if you want to. So writing down our equation relating torque, moment of inertia and angular acceleration, we have tau equals I alpha. Substituting in the numbers gives 5.8 times 10 to the 7 times negative 6.7 times 10 to the minus 3, and putting that into your calculator should give you an answer of negative 3.9 times 10 to the 5 Newton meters. And again, you don't need the negative to score the marks here, but technically it would make sense to be negative because the rotor assembly is coming to a stop. So the unbalanced torque is acting to slow it down. Part C says in winter, ice forms on the rotor assembly adding mass to the blades. As the temperature rises, ice can be thrown from the blades. Part 1 says on the diagram shown in figure 3b, show the direction of the initial velocity of a piece of ice thrown from the tip of a blade at the bottom of its circular path. And there's 1 mark available here. Well, for a blade at the bottom of its circular path, that would be this blade here, and to show the direction of the initial velocity of the ice, it would look something like this, so it would be a horizontal line moving to the left, since the direction of rotation is clockwise in this question. So the ice is going to move off at a tangent to the tip of the blade. C part 2 says as a result of the ice being thrown, mass is removed from the blades. Explain why, despite this loss of mass, there is no observable change in the angular velocity of the rotor assembly, and there's 1 mark available here. Well, we can simply say here that the mass of the ice is negligible, or in other words, it can be ignored. Lastly, part D says the maximum power P generated by this wind turbine is given by the following relationship. P equals 0.3 rho AV cubed, where rho is the density of air, which equals 1.29 kilograms per meter cubed, A is the area of the circle swept by the rotor assembly in meters squared, and V is the wind speed in meters per second. Calculate the maximum power generated when the wind speed is 11.5 meters per second, and there's 2 marks available here. Well, this is an unseen formulae question, so all we need to do is sub the numbers into the right place. So we have P equals 0.3 rho AV cubed. Substituting in the numbers given to us, we have 0.3 times 1.29 for the density, times pi times 54 squared, where pi r squared is the area of a circle, so we're just taking pi times the radius squared, where 54 is the length of one blade, i.e. the radius of the circle, times the velocity cubed, where we're given the velocity here is 11.5 meters per second. So putting that into your calculator should give you an answer of 5.4 times 10 to the 6 watts. That's all for this video, folks. Thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video one of these, subscribe to the channel, and I'll see you in the next one. Take care.